Sine 2u is literally just the sine of u plus u, right? That'd be sine 2u. We already know a sine addition formula. Our sine addition formula is sine a plus b is sine a cosine b plus cosine a sine b. Sine, cosine plus cosine sine is the succinct way that we've been saying it. So if I go through and I put u in for a and I put u in for b, again over here u in for a, u in for b, u in for a, u in for b, I'm going to end up with 1 sine cosine plus 1 sine cosine. That would be 2 sine cosine. And that's exactly what this formula is. I could do the same thing with cosine double angle. Right? Remember our cosine addition formula is cosine cosine minus sine sine. So cosine cosine, that'd be cosine squared, minus sine sine, that'd be sine squared. We could do the same thing with our tangent formula down here and do tangent u plus u, and it would create this formula. Now, you notice that we have 3 different formulas for cosine 2u. We talked about how we got that first one. These other 2 come from the Pythagorean identity that we already know, sine squared plus cosine squared equals 1. Because you'll notice that if I took cosine squared minus sine squared and I replaced sine squared with its Pythagorean identity, that's 1 minus cosine squared. If I replace sine squared with 1 minus cosine squared, distribute that negative, and you'll have cosine squared minus 1 plus cosine squared. So that would be 2 cosine squareds minus 1. So that's where this formula comes from. It just comes from manipulating that first one. Same idea if I took that cosine squared minus sine squared, that same starting formula from up here. If I took that formula and this time I replaced cosine squared with its Pythagorean identity, 1 minus sine squared, then I'd have 1 minus 2 sine squared. And so that's this alternate formula up here as well. So you can memorize those 5 formulas, or you can create those 5 formulas, whichever way you want to go. Bottom line is we need to know them. Now something they stress to me over here is that when you see sine 2u, that is not the same thing as 2 times the sine of u. I can't like factor that 2 out to the front or distribute that 2 to the u or anything like that. Throw a value in there, like let's say 45. If you put 45 in there, what this would say is the sine of 2 times 45, so that would be the sine at 90. Sine at 90 is 1, right? Whereas if I put 45 in here, I'm going to get the sine of 45, which is square root of 2 over 2, and then I'm going to multiply that by 2, which is square root of 2. They're not the same thing. So they stress that to me there. All right, so let's start with our first example. These little numbers in red are, again, homework problems that correspond to the example that we're looking at. All right, so for this first example, they asked me to find sine 2 theta based on the information from the triangle. So we said just a moment ago that the formula for sine 2 theta was 2 sine theta cosine theta. So right up here, sine 2 theta is 2 sine theta cosine theta. Variable doesn't matter. You can use u, theta, x, y, whatever you prefer. So now I need to figure out what the sine and the cosine are. So I'm going to come over here to my triangle. If this is 3 and this is 4, what's this guy?
5.
5, right. That's that 3, 4, 5 triangle. So looking at that triangle, I need the sine of theta. So here's theta right here. What's sine going to be? 3/5, right. Opposite over hypotenuse, 3/5. What's cosine going to be? 4/5. Adjacent over hypotenuse, exactly. So I'm going to put those values in, that same thing that we have been doing now since section 4.3, where we built the triangle and we pulled values off the triangle. So once we get this formula, we're back to stuff that we've been doing over and over again for the past month.
So is that triangle given?
Mm-hmm. The triangle was given. Mm-hmm. All right, so then we're going to multiply. So 2 times 3 times 4 is going to give us 24, and 5 times 5 is going to give us 25. And that's all there is to it. Just plug in numbers into the formula. All right, let's look at example 1. For example number 1, it says, find all solutions of 2 cosine x plus sine 2x is equal to 0. So I want to solve this guy, right? Now, remember when we solved double angle problems? Because I got a double angle right here. I have a single angle right here and a double angle right here. Remember when we solved double angle problems, we had to do all kinds of extra crazy stuff. That was where we had to go through, and instead of solving between 0 and 2 pi, we had to change it to 0 to 4 pi. And then once we got, all of those answers, then we had to go through and cut each of them in half. And I mean, it did not work like a normal single angle problem, right? You cannot then solve a single angle and a double angle at the same time. They don't solve the same way. So anytime I have a problem that has a single angle and a double angle in it, I got to get rid of one of them. I have formulas for double angle, right? So let's get rid of that one. Let's replace sine 2x with its formula, 2 sine x cosine x. All right, so as we've been going through, anytime we were working with a trig function that looked a little confusing to us, we would substitute out the trig part. So I'm going to replace cosine with x, and I'm going to replace sine with y. So if I was given something like this and told to solve it, I would go through and take out a common factor of 2x, right? And that would leave me with 1 plus y as my other factor. And then I could set each one equal to 0. So we're just going to do that exact same thing for our problem. We're going to go through and take out a common factor of 2 cosine. And when we do, we'll be left with 1 plus sine. And then we could set each of those equal to 0. So the exact same way that we worked it out with x's and y's, we can do with sine and cosine. Okay, so I got to get cosine by itself over here, so what am I going to do? Divide by 2. And how about getting sine by itself here? Subtract 1. So where is cosine equal to 0? Yeah, you're both right. Pi over 2 and 3 pi over 2. Where's sine equal to negative 1? 3 pi over 2. Now, on every single one of the homework problems and on every single one of the test and quiz problems, we are always going to have the restriction to only give answers between 0 and 2 pi. So these would be our answers. I don't have to write 3 pi over 2 twice. I can just say x equals pi over 2 and 3 pi over 2, and I'm done. However, if you're looking back over this example in the book later on, you're going to see a different answer, and I want to explain to you what they've got and why they got it so that it might not confuse you later on. So we've seen before that if we did not have the stipulation of only finding answers between 0 and 2 pi, that we would have to find like every solution on the face of the earth, right? And so we basically said that the solutions would happen at pi over 2 and all of its coterminals. And so we had said an easy way to address that was just take each of the answers that you got and tack on a plus 2 pi n after it. Because what that does is it says, hey, n could be 0, which would just give me pi over 2. N could be 1, which would be add 2 pi. N could be negative 1, which would be subtract 2 pi. And we could keep going in both directions infinitely. That would be every coterminal on the face of the earth. So by adding that plus 2 pi n onto the end of each of our answers, we address every possible answer on the face of the earth instead of just in the restriction 0 to 2 pi. For this particular problem, they're able to take those two answers and condense them down even further, and we've not seen this before. The way that they can do that is, if you'll notice, pi over 2 and 3 pi over 2 are exactly 1 pi apart. So if you come around this way or you come around this way, they're always 1 pi apart. That's not always the case. I mean, sometimes I get an answer in like the first quadrant and the second quadrant, and there's no way to condense that down because they're not an equal distance apart every single time. Where, you know, the distance from the first quadrant to the second quadrant wouldn't be the distance from the second quadrant all the way back around to the first quadrant again. But for this particular case, the distance between pi over 2 and 3 pi over 2 is 1 pi. And then add pi and you're back up here, and add pi and you're back down here, and add pi and you're back up here. So what they've said is we could write both of these just with one statement, and that would be start at pi over 2 and add any multiple of pi. And that would give you all of the coterminals for both of them. Okay? So again, when we do this for the homework, for the test, for the quiz, we are going to give our answers like this between 0 and 2 pi. We're not going to do this, but I just wanted to explain to you where that was coming from when you see it in the textbook. All right, example number 2. Example number 2, they asked me to graph y is equal to 4 cosine squared x minus 2. I don't have a clue how to graph that. Okay, I know that 4 changes the amplitude, and I know that 2 down there causes a shift, but I've never learned how to graph cosine squared. What am I supposed to do with that? Well, the fact that it's in this section kind of gives us an idea that maybe we could use these formulas up here on the top of the page to help us. And so what we want to do is use those formulas to help us rewrite this formula into something that we do know how to graph. So again, if I were starting with this and I just wasn't really sure what to do, I could come over here and substitute out the trig stuff and say that's 4x squared minus 2. So if I had something like that and I was solving it, I'd go through and I'd take out the common factor of 2, and that would leave me with 2x squared minus 1, right? So let's do the same thing with this guy. Let's take out the common factor of 2, and that'll leave us with 2 cosine squared minus 1. So the same way that we did it with x, we can do it with cosine. And now if you'll notice, 2 cosine squared x minus 1 is one of our identities. It's cosine 2 theta, or cosine 2u, or cosine 2x, whatever variable you're working with. This, I know how to graph. 2 cosine 2x. Let's start with our normal cosine curve. So I've given you the normal cosine curve here just as a reference. You wouldn't have to graph that. What's that 2 out in front going to change? Amplitude, right. So it's going to go twice as high and twice as low. So there's y equals 2 cosine x. All right. Then what's this 2 going to change? The period. So remember that our new period is going to be the original period divided by the b value. So that means that our new period is going to be 1 pi. So that means that I have to be done drawing this entire red curve by the time I get to pi. So I'm going to draw that exact same curve but be done by the time I get to 1 pi. Another way we talked about that is put 2 in the same amount of space you normally put 1. So there's 1, 2 in the same amount of space that we normally put 1. So good review for us of that graphing that we did at the end of chapter 4. All right, then example number 3. It says, use the following information to find sine 2 theta, cosine 2 theta, and tangent 2 theta. And they give me some information about cosine. So they tell me cosine is 5/13, and theta is in between 3 pi over 2 and 2 pi. And they want me to find sine 2 theta, cosine 2 theta, tangent 2 theta. All right, to find these guys down here, I'm going to use those formulas from the top of your note sheet. I'm going to need to know what the regular sine and tangent values are. So let's go ahead and find those. First off, what quadrant am I in? Fourth quadrant, right. They told me that theta was between 3 pi over 2 and 2 pi. So I'm in the fourth quadrant. That's important for me to know whether these values are going to be positive or negative. So I can come over here. 5/13 is not a value that we've memorized off of the circle. So we're going to build it with a triangle. So we can come over here and say, okay, cosine is adjacent over hypotenuse. Have you seen it enough to know what this other side will be? Yes, good. That's a 5, 12, 13 triangle. Only thing is I don't really know if it's positive or negative. It's the y value, and I'm in the fourth quadrant, so it's going to be negative. If I didn't pick that up while I was building the triangle, it's not a problem because I can fill it in when I get over here to calculate my values. All right. So let's find sine. So looking at our triangle, here's theta. What's sine going to be? Negative 12/13. Perfect. All right, what's tangent going to be?
Negative 12 over 5.
Negative 12 over 5. So again, if I didn't know whether that 12 was positive or negative from my work down here, once I got over here, I could say I'm in the fourth quadrant. All students take calculus, only cosine's positive there, so that would mean my cosine's positive, but my other two are negative. So I could just fill it in there. Okay, So now we're ready to find sine 2 theta. So we're going to use that formula that they gave us at the beginning, 2 sine theta cosine theta. All right, so what did we find the sine to be? Right up here, negative 12/13. And cosine was given, it was 5/13, right? So exactly like we did in the very first example today, I'm going to go through and I'm going to say 2 times negative 12 times 5 is negative 120, and then 13 times 13 is 169. All right, we have 3 different formulas for cosine 2 theta. If the first row used the first formula and the second row used the second formula and these last 2 rows used the third formula, we'd all get the same answer. It does not matter which one you use. I'm going to go back to my practice of only using the given information anytime that I can. So since I have 3 different formulas for cosine 2 theta, one of them only has a cosine in it, right? And cosine was given. So I'm going to choose that one. That way, if I've messed up my sine value, I won't then mess up my cosine double angle. But you could use any one of those 3 formulas. All right, so cosine was given as 5/13. Only thing I have to be careful of here is just order of operations. So I'm going to square the 5/13 first, and then multiply it by 2. And when I do, I'm going to get 50 over 169. The only way to combine that with this 1 is if I have a common denominator. So while I'm at it, I'm going to rewrite 1 as 169 over 169. And then I can subtract with that common denominator. So there's cosine 2 theta. Tangent 2 theta, I only have one formula. So that's pretty easy. I'm going to use the one that's given. And I'm going to replace tangent with what it's equal to, negative 12/5. So I'm going to have 2 times negative 12/5 over 1 minus a negative 12/5 squared. Let me tell you one of the most common mistakes that I see on the test. With this type of problem, what students try to do is they try to just replace theta with negative 12/5. So they come down here and they've got like 2 times the tangent of negative 12/5. And then they're stuck. Like, what am I supposed to do with the tangent of negative 12/5? It's the whole tangent theta that's equal to negative 12/5. So I'm going to replace the whole tangent theta with the negative 12/5. Replace the whole tangent theta with the negative 12/5. So once I put those numbers in, there shouldn't be any trig functions left. It should just be simplifying simple algebra. Okay? All right, so again, got to do order of operations here. So in the bottom, negative 12/5 squared is going to give me a positive 144 over 25. And then I would have 1 minus that. Going to need a common denominator, so while I'm at it, I'll just write the 1 as 25 over 25. In the numerator, I took 2 times negative 12/5, and I've got negative 24 over 5. All right, so when I subtract down here in my denominator, I'm going to get negative 119 over 25. So right now I have negative 24/5 divided by negative 119 25. When you divide fractions, remember you multiply by the reciprocal. So I'm going to change division to multiplication, and I'm going to give the reciprocal. So keep, change, flip. Cancel anything we can to help us reduce. And there's our final answer. Now, remember how tangent is sine over cosine? Tangent 2 theta is sine 2 theta over cosine 2 theta. So here's something cool that you can do. You can take the answer that you got for tangent, and it should be equal to the answer you got for sine divided by the answer you got for cosine. Again, when I'm dividing fractions, I multiply by the reciprocal, but sure enough, you'll notice that I get the same thing. So that just gives me a fast, easy way that I can check all 3 of my answers at one time and know that I'm on track. Okay.